way in which a transfer function behaves when we factor that. So this is the numerator, this is the denominator. And the various time constants that we can factor out there, if we can do this, if we can factor the denominator into terms of that type, which have real time constants, then we will have a root at that point which is associated with that factor. Right, so we have real root of 1 over tau, which is associated with a time constant of tau. In some cases, we are unable to factor the polynomial into a form that has real coefficients. And in those cases, in general, we don't do that. We don't actually do the factorization. We keep those terms separate. And so that's now where we have something like tau squared s squared plus tau zeta s plus 1, right? And these roots may end up over here. Kind of summarize the whole of this plane by saying on this line, that's where responses like this live. On this line is where responses like this live. And up here is where oscillatory responses live, while over here is where oscillatory and increasing responses live, right? So that's basically everything that you need to know. Oh, very important, right on that plane is where pure sinusoidal responses live. Okay? And so you can kind of broadly cut this into stable and unstable. And stable, our kind of conventional working definition for what a stable response is or what a stable system is a system that if I change the input in a bounded way, I end up with a bounded output. And so what does bounded mean? It just means that I can draw lines that that output will never cross horizontally on the y, right? Whereas over here, there's no line that I can draw. For an unstable process, there's no line that I can draw that will never be crossed. I can take any kind of magnitude away from the initial point, and an unstable response will eventually go outside of that. Now, we talk about stable systems in this kind of way, where we say specifically that, that's very annoying. We say specifically that we're talking about a bounded input because obviously any system can be made to move in an unbounded fashion as long as I apply an unbounded input. In other words, it's kind of not fair to say, what if I subject the system to a ramp input? Well, if the ramp input is unbounded itself, it's kind of very easy to expect that the output of the system will also change in a bounded way. So we have this kind of bounded to bounded definition of stability, and under those definitions, stability is completely determined by the poles of the transfer function, right? But, of course, I've now put here a 1 over there. There are more systems than these kinds of systems, right? There are also systems with zeros. Now, we talk about poles and zeros, so the roots here of the denominator, they are called the poles. And you'll see that we often do this. We often factor the polynomial slightly differently to accentuate the fact that we are defining these zeros or the roots of that polynomial as interesting points. So here I've factored, and we can take any rational function, and on the standard forms, we specifically made it happen so that the coefficients are 1, and the reason why we wanted the coefficients or the constants to be 1 is so that we could use the final value theorem very easily to determine the gain of the system, right? But that form doesn't make it easy to determine the poles and zeros, and we're discovering now that the roots of these polynomials are particularly important. And so when we want to think about the roots of the polynomials, we would like to factor those polynomials into this form where the roots are clearly visible, right? So in this form, the roots, every time one of these, every time s becomes equal to, so in this form, if s is equal to z1, the denominator or the numerator is 0, right? If s is equal to z2, the numerator is 0. So anytime s becomes equal to one of these constants, that's effectively the a0 of that polynomial, or a root of that polynomial. So effectively, I've just factored it so that the roots are basically visible directly as the coefficients. So notice the negative sign, and notice the fact that the s has a unity coefficient. So this form, where I've factored in such a way so that I can easily see the poles is very easy so that I can interpret this. But what happens when my function has zeros? Now, I would like you to think about this. The textbook, and just a note here, the textbook kind of doesn't actually explicitly give you any machinery to interpret numerator, what is called numerator dynamics. In other words, what if the numerator is not just a constant? And I want to give you a way of thinking about this that is more than just memorizing standard forms. So the way I want you to think about a system with a 0, and I'm just going to start with a single 0, in other words, a first order numerator. So if I have a system like this, and I've got other stuff happening over here. Here I have a stable system. I have a stable system. I know it's stable because the roots of the denominator, or the poles, are in the left-hand plane. I expect that if I were just looking at this close relative of this function, in other words, a function that looked like this, I could easily sketch out the step response of that system by seeing that that is an overdamped second order system. Right? Does everybody see why? I've got real roots in the left-hand plane, so I effectively have time constants of 1 over 1 and 1 over 2. So I've got those two separate time constants, and so I expect that that transfer function would have the characteristic second order S-like step response. Right? Now, so we can see that there's kind of a family resemblance there, right? They share denominators, and therefore they share stability characteristics, and I've been speaking about how you can kind of infer the impulse response a little bit from looking at just the locations of the poles. The poles are incredibly important because these are the things that make the transfer function infinite, that make the Laplace transform infinite, which is where we expect maximal similarity. The zeros obviously make the Laplace transform 0, and that's a little bit harder to interpret. I'm going to give you a way of interpreting it now. What we're going to do is we're going to multiply that out, or we're going to separate those two factors. And I want to show you that I can factor this out as that same G. Let's call this G2. Right? Now G1 I can actually rewrite as S times this minus Z times this, which is basically S times G2 minus Z times G2. Because the numerator allows me to do this, I effectively say, right, if I know what G2 looks like, if I know what the step response of G2 looks like, and I am relatively adept at calculating derivatives in my head, in other words, sketching the derivative of something, which you should be able to do. In other words, if I look at that, so if that's the G, if that is the step response of G2, I should be able to imagine what the derivative of that looks like. Right? So we know that while the function value starts, so if I look at that second order system, while the function value starts at 0, and then kind of, and the derivative also starts at 0, right? It then rapidly reaches a maximum. The derivative becomes large, and then again becomes small, remaining positive all the time. And so I can say that the derivative of that signal would look like this, with that maximum point over there corresponding with that inflection point over there. And so by this point, I'm actually done, right? Because I now know that the response of this system with numerator dynamics can be completely explained by understanding the denominator dynamics and then doing a couple of extra derivatives. Does everybody see how that relationship works? So this is how you would do this if you were doing it in your head, is you would be thinking, right, I'm going to see some amount of the kind of system that was G2, and that amount is going to be given by the magnitude of the 0. In other words, if the 0 is itself close to the origin, in other words, if z is close to 0, I'll effectively only see the derivative. I'll see just this, I'll see this effect only. While as that number gets bigger, I will see a larger effect of just this system without the numerator dynamics. But notice, I'll see it going down. Right? So you can see for systems like this, with a minus z over there, if that z is positive, the overall gain of the system will actually be negative. Well, it won't necessarily be negative. You'll have to kind of work it out with all these other factors as well. This factorization doesn't make it easy to work out the gain, but the contribution of that term is negative, while the contribution of the derivative is positive in this case. Now, this works all the way through. So if I have higher order numerators, I simply multiply them out, and then I'll find that there will be a reference to the second derivative and the first derivative and the constant, or the third derivative, and so on. And as the order in the numerator increases, I will see behavior that I would associate with the derivatives of each of these systems. And so that's kind of the one thing that I want you to understand, is that numerator dynamics add no new special behavior, right? If I know the denominator, the stability is never affected. The stability of a system is never affected by the numerator, because I always start with that kind of base. Furthermore, if I have something like oscillatory behavior, you can't derive out oscillatory behavior, right? So if I have a numerator with roots in with complex roots, taking the derivative of a signal like that, which is oscillating, just results in another oscillatory system. So that family resemblance will always be there, regardless of how the numerator is chosen. Right? So the denominator completely determines the dynamic nature, kind of that family resemblance, the family of E that is the solution to the differential equations. Adding stuff onto the denominator just complicates the calculation, but it complicates it in this very specific way, that we only add effectively references to the derivative of that original base exponential. And so that never changes the frequency of oscillation. It never changes the nature. It doesn't change whether the system oscillates or whether it doesn't oscillate. It doesn't change stability. So you can't take an unstable system and by adding the derivative make it stable, right? It's always like that instability is always going to be there. So that's the first thing that you need to understand about interpreting numerator dynamics. And please note that this thing that I've just shown you is not explicitly mentioned in the textbook. So this is kind of, in terms of interpreting this kind of stuff in your head, that's how I want you to think about this. But there is one very special case where numerator dynamics has a very easy and specific interpretation. Now this is in the textbook, and it arises, the easiest way to think about it arising is, what happens if I add two first-order systems together? In other words, what happens if I have a system that I build by I take an input, I split it into two, and I have a first-order system added to another first-order system. That's going to result in, and so what I see is, if I simplify that, I end up with a time constant here of k1 tau 2 plus k2 tau 1 s plus k1 plus k2. And now this is all very well and fine, not any kind of big deal. If I know that this is going to be a step input like this, I know that the step response of that first order system, that first order system will have a step response something like this, and the second one will have a step response that is similar, and I expect quite similar behavior to that sum. So I expect some kind of also somewhat exponential kind of function to appear in the overall step response. But things are not as easy as they appear, because specifically if one of those gains is, or if the gains have different signs, and so without loss of generality we can assume that K2 is negative. So what happens then? What happens if I'm not just adding two nice positive gain systems together, I'm actually having one positive gain system and then I'm subtracting another system from it. What happens then is I can actually end up with something where I've got a first order system like this, and I'm subtracting, or actually it's easier to kind of imagine when I draw it negatively. I'm subtracting something that looks like this. And under some specific conditions, what that means is this system, if that system is reacting, if the time constant is quite slow, I can end up with a condition where initially the output starts going up. And if this gain, if this magnitude is quite large relative to this one, right? In other words, if that magnitude is going down, let's say that's going to 1, and this is going down to -2, the net effect will be negative. Now this thing that I've just explained here, or this thing that I've just shown you, could happen, right? If I just adding two first order systems together, and you just in your mind need to distinguish between multiplying them together and adding them together, right? But we've added two first order systems together. Adding two first order systems together gives me a second order denominator, right? Which we see. And it has numerator dynamics. And this thing under these particular conditions, which I'm not going to go into a great deal of mathematical detail into, but which you can go and look at the exact bounds in the textbook, is known as inverse response. The reason why it's known as inverse response is the initial behavior appears to be positive gain. In other words, I've changed my input in an upward direction, the output is moving in an upward direction. But the eventual gain, the true gain of the system, is different. So it's a bit tricky, this kind of process. It's almost like fainting. Like if you're trying to get past somebody on a rugby field or something like that, and you kind of first move left and then go right. Now, the same kind of thing can happen if you're trying to interact with these systems. In other words, if you think, oh, I'm just going to see what happens. I'm going to turn this knob and see whether the gain is positive or negative. And you don't wait a long time, and you say, oh, okay, well, I turned the knob up, and it started going up. So obviously this is a positive gain process. If you don't wait for that negative behavior to come in, you could be fooled into thinking that this is a positive gain process. And so this is very tricky, and it's a very undesirable behavior for systems to have. So it is very good for us to kind of figure out when exactly this will occur. And I can tell you that the easiest, because you can interpret this, you can go through all the derivatives and so on, but luckily we have an easy rule for inverse response, which says that inverse response happens under these particular conditions. If I have a right-hand plane 0 and a numerator less than the denominator order. So under these conditions, if I have a 0 in the right-hand plane and I have kind of a normal system, the kind of system that you would have here, in other words, two first orders added together give me a first order over second order polynomial, and because that first order is less than the second order, and because I can now locate, if I have that pole or that 0 in the right-hand plane, I will observe that the step response of the system will exhibit inverse response. In other words, it will go up before going down or down before going up. We still use all the normal rules for determining the eventual gain. So we can still just substitute s equals 0 into that transfer function to figure out what the final gain is, but we can't do that for the initial behavior. The initial behavior, to determine what direction the initial behavior is going, you can go and calculate the derivative. But in most cases, what we're kind of trying to do is just figure out whether inverse response exists. So if I know that I have inverse response, I know that the initial behavior is going to go in the opposite direction. Okay, so that's the first kind of thing of numerator dynamics. So qualitatively, a good way of thinking about numerator dynamics is this way that I've just explained, where we take, if you're thinking about it, remember that the numerator can always just be multiplied out, right? And so every time you multiply by s, you're taking the derivative. So if you have a second order numerator, you'll have to take into account the system behavior, or let's say the pole behavior, plus the behavior of the pole's derivative, plus the behavior of the pole's second derivative. And the amount of each one of those that is contributing to the final behavior is given to you by the coefficients of the polynomial, right? And so what that means is if you have small time constants in the numerator, the behavior will basically be dominated by the just the pole behavior. If you have large time constants in the numerator, the derivative behavior will dominate or will become more pronounced. Then there's this one specific special case that you have to take special cognizance of. You have to know that this is a very special thing that can only happen. This idea of inverse response cannot happen if there are no s's in the numerator. Right? So every other kind of system, so systems that have many, many poles but no zeros, right, can never do this. They can never kind of start out one way and then go the other way. They always, because you're just adding all of those exponentials together and all of those exponentials start the same way, you can't ever get any different behavior than something that starts out basically in the same direction as its eventual gain. An important thing to note while I've got this up is I expect you to be able to do this both ways. In other words, I expect you to be able to look at a transfer function and predict whether inverse response has happened by calculating the roots of the denominator, of the numerator, I'm sorry. And I also expect you to do this by looking at a response and recognizing inverse response from a sketch, and then inferring that one of the numerator roots must be negative. So both of those I expect you to be able to do. Now there's another piece of dynamics which completely rounds out everything that we know about transfer functions. And that is, sometimes transfer functions are not rational functions. And this specifically happens when there are time delays in the function. So earlier I said a general kind of form for G was S minus Z1, S minus Z2, and so on, over S minus P1, S minus P2, and so on. But this is not the 100% story, because from time to time, and quite often in chemical engineering systems, we will also have one of these. Now that exponential term arises from transport delay in the system. So it arises from situations like, I've got a tank over here, like the tutorial that we did. I've got some very long pipe connecting it to another tank over here, and I'm perhaps taking the temperature here and suddenly increasing the temperature. Now it actually takes time for the hot stuff to move from here to here. And if we assume that that plug is just nicely insulated and no back mixing occurs and all the kind of stuff that you do in piping, you can kind of imagine that there's just a slug of hot stuff that just moves unchanged through to this. So in other words, you can basically say that if I have a T over here, the temperature here will actually be T minus D. Okay, so this is called a transport delay. This particular idea, which is if the delay is associated with stuff moving from one point to another in a pipe, it's very often modeled in this way, where we just have a pure delay. And the Laplace transform of this delay is this e to the minus ds. And this is just, it is a rule, right? It comes from the fact that the Laplace transform of f of t minus d is equal to f of s times e to the minus ds. And this is in the table, so you don't have to memorize that, but you'll find yourself remembering it because you're going to use it a couple of times. And so time delay throws a bit of a spanner in the works. It causes many difficulties. On the one hand, it causes difficulties because it makes systems a lot harder to control, which we'll be talking about in much more detail next semester. But specifically for us, it also makes all of our calculations significantly harder. Most importantly, that because this exponential is not a polynomial, it is no longer trivial to determine the roots of the numerator and denominator polynomials. It becomes hard. Now, if we imagine that to be in the numerator, you can kind of ask yourself, but why would that term mess with the poles of the system? Now, it doesn't if it's a pure dead time just lashed on like that. But by the time I start adding systems together and calculating the effect of feedback loops, I very quickly start having exponentials in the numerator, in the denominator. And that messes with my pole calculations. So it is relatively easy to calculate the poles or the roots of polynomials. We have very strong guarantees about how many of them there will be. If I know that I've got a second order polynomial, I know that there will be exactly 2 roots. If I have a 5th order polynomial or a 100th order polynomial, it's called the fundamental theorem of algebra. We know that a polynomial has as many roots, exactly as many roots as it has order, right? And so we can make some very strong guarantees, and there are thousands of theorems about locating those roots. So there are theorems that allow us to figure out whether the roots are to the left or to the right of the complex plane or of the complex line. There are theorems that allow us to count how many real roots there will be between an interval or something like that. All of those theorems can be used to great effect to calculate the poles and therefore to figure out what the dynamics of the system will be. Unfortunately, as soon as there is a non-polynomial element, all those bets are off. Right? So there's no general theorem that allows us to figure out how many roots a general nonlinear equation has, or a function like this, which is the sum of a polynomial and an exponential. And so in many cases, and we'll talk about that in the next lecture, we will be forced to approximate this behavior with a rational function. And that's kind of the topic of the next lecture. Now, okay, that is basically what I wanted to say today. So this is now the full version of transfer functions. Every transfer function that we will be working with in this subject not quite, is some combination of these kinds of terms. Right? So in other words, every sub-transfer function will be of this form, but we may see things of this form added together. We may see things of this form divided by one another and so on. Right? But so if that's the prototype of our functions, or that is effectively everything that you will ever see in the Laplace domain, is polynomials or e's. For linear systems, that's kind of the entire world. We're going to rapidly try and approximate that E. And tomorrow, I just want to, there is good news. I will not be in class tomorrow. I will be attending our graduation ceremony. I have master students who are graduating, so I want to see them get tipped on the head. However, I will be recording a video for you to review during that lecture time, which is about approximation of higher order systems by lower order systems. Because you can now see we started with simple systems, and we've gone more and more complicated. We've added more and more terms in the numerator, and now I've added terms in the denominator, and I've added exponentials. And wouldn't it be nice if we could just go back to the simple times of first and second order systems? And the answer is yes, and we can, but we can't do that exactly, but we can do it approximately. So there are ways that we're going to use to approximate those higher order systems with functionally equivalent low order systems. And that's basically what the video is going to be about. Thank you very much for your time. I will therefore not see you again this week. I will be on Slack basically for the rest of the week. We will see each other again in person on Monday.